Hello, I am Orestes Salpos and I'm excited to present you our work How to Trust Strangers, Composition of Byzantine Quorum Systems. This is joint work with Christian Cashan and Luca Zanolini from the University of Bern. This work concerns trust assumptions. The trust assumptions of a distributed system specify which processes are expected to fail during an execution, and by extension they specify the resilience of the distributed system. The trust assumption can be expressed in the threshold model, where the algorithm specifies that it can tolerate up to f failures, which could be, for example, that the f is smaller than n over 3, with n being the total number of processes. Or, of course, they could also be generalized, and usually these generalized trust assumptions are expressed by a Byzantine quorum system. Now, there is some theory behind Byzantine quorum systems, but for this presentation, the important is to have in our mind that it is based on a fail-prone system. The fail-prone system is a collection of fail-prone sets, and each fail-prone set specifies the processes that can at most fail during an execution. And what's important about the fail-prone system is that it must specify the Q3 condition in order to be able to define a quorum system on top of this, the fail-prone system. The Q3 condition says that any three fail-prone sets must not cover the whole set of participants. And what we just talked about is the symmetric model of trust. Symmetric because all participants, all processes accept a global, a common fail-prone set F. However, it can be the case, and there are models that express this, where every participant specifies their own fail-prone system. And this is the model of asymmetric trust. And formally, this has been defined by Cashan and Tachman, and it's based on an asymmetric fail-prone system. The asymmetric fail-prone system is just the collection of all these fail-prone systems that are specified by each of the participants. And similar to the symmetric model, here we also have a condition called the B3 condition, which it's not important to have the exact formula for this presentation, but it is more complex than Q3. And at this point, you would agree with me, you would probably agree with me that especially asymmetric Byzantine quorum systems are hard to design, exactly because now we allow the participants to specify their trust. So it's actually quite hard to achieve, to satisfy this B3 condition. And it's an open research question. What happens if the B3 condition is not satisfied? Which processes change the trust assumption? So it's very hard to satisfy this condition, but on the other hand, it's necessary if we want to reach a global agreement. And in this work, we make a step towards making asymmetric BQS more practical. And specifically, we explore and show how we can combine existing asymmetric and symmetric Byzantine quorum systems. It's important here to mention, however, that what a non-solution would be. One might think that we can take the set of participants, join them together, and then let them figure out some new fail-prone set, some new trust assumptions in the resulting system. But of course, this would result into the problems we talked about earlier, namely the hardness to satisfy the B3 condition. Instead, what we want to do is to start from the existing fail-prone sets and in a deterministic and non-interactive way end up with a new Byzantine quorum system that, of course, satisfies the Q3 or the B3 condition in the asymmetric case. That said, we can start with an example in the symmetric case first. So here we have two BQS defined on two sets of participants, P1 and P2, P1 contains the processes A, B, C, D, E, and P2 contains the processes D, E, F, G, and H. And here on the slide we can see the favorable sets of the two systems. For example, the first BQS has A or BC or CE or D as favorable sets. A first idea would be what we call the union rule, to just take these two favorable systems and take the union, and thus we come up with a new favorable system. Indeed, this works in the sense that it leads into a Byzantine Quorum system, but it does not tolerate many failures. Namely, it doesn't tolerate any combined failure between the two sets of participants. So we want to find a better rule. Our second idea is to take the pairwise union of every favorable set in the first and every favorable set in the second set of participants. This works in the sense that it leads into a favorable system that tolerates more failures, and we prove in our work that if the two sets of participants are disjoint, then also the Q3 condition will always hold. However, in this example, we can observe that these three sets that we see here will be among the created favorable sets. Now, what is the problem with these sets? They cover the whole universe. If you see, they contain all the processes in the composed system. Thus, the Q3 condition is not satisfied. Now, why this happens? If we observe the last of these three sets, CED, and take the projection of this in the first in P1, which is CED, then we observe that this is not a favorable set. If we take the projection in P2, which would be ED, then again this is not a favorable set. DE is not tolerated in the second system. So in some sense we have come up with a favorable set that was not there in the original systems. So in order to correct this rule, we will take again the pairwise union, but with a special handling in the case that if these two favorable sets contain common processes. Namely, if they contain common processes, we don't take the union of these sets, but only the union of their subsets which contain exactly the same common processes. And we can depict it like this. The dashed lines imply this special handling when taking the union of the two favorable sets. And shortly, an intuition of why this works is that if a process is Byzantine in the first system, then it is actually Byzantine in the second as well. It's the same process after all. So if a fail-prone set in the first system contains it, then it has to contain it. Also, the fail-prone set in the second system has to contain it. And the result of applying the final rule on our example would be the fail-prone sets that we see here. And we prove that this rule always leads into ABQS. It always satisfies Q3 condition. And it also tolerates as many failures as possible, always given the restriction that we don't want processes to come up with new assumptions in the resulting system. Okay, we can now switch to an example in the asymmetric trust. We said that in the asymmetric trust, every process has its own fail-prone system, and this is what we can see on this slide. We have two sets of participants, again, P1 and P2, with A, B, C, D, E in the first, F, G, H, I, J in the second. Here we choose disjoint systems just for simplicity. And let's take, for example, process C. Its fail-prone system contains the sets A, B, or D, or E. And we would like here in this asymmetric model, we would actually like to use our results from the symmetric case. So how could we do this? We could have every process apply the Cartesian rule between its own fail-prone system and some fail-prone system of the other ABQS. So, for example, process C would have to do something like this. But then the question is, what fail-prone system do we use for the second ABQS? It would be nice if we could have a summary, a top-level view of this ABQS. And this is a main contribution of our work. And in order to explain it, let's think again what an ABQS is. In an ABQS, every process can freely choose their assumptions. They can choose their angels, demons. And in this sense, no global notion of correct or bad assumptions exists. However, what does exist, what we have as ground truth in every execution, is the actual set of Byzantine processes. For example, in an algorithm with asymmetric trust, this could be an execution among 7 processes. The processes are here depicted by the colored circles. And in this execution, maybe the red and the yellow processes were Byzantine. And as a result, the first 3 processes have correctly guessed, have anticipated the failure of the red and yellow processes. And for this reason, they are wise. We call them wise. Similarly, the black process is wise, but the pink process didn't anticipate the failure of this specific set. So it is a naive process. What is more, the first 3 processes together form what is called a guild. Now, a guild is a set of processes such that they are wise, but also they have enough wise friends in the guild. Recent results in the literature show that the existence of such a guild is necessary for the properties of consensus to hold. Kazan and Giannolini prove that in every execution with a guild, the properties of consensus will be satisfied for all the wise processes, not only the wise processes in the guild. And also other lines of work, such as Stellar, for example, condition the properties of their algorithm on the existence of such a set. They don't call it a guild, but again, it's a set of well-behaving participants who have enough well-behaving friends inside this set. For this reason, we come up with the definition of the tolerated system of an ABQS. And in order to construct this tolerated system, we consider every possible failure in the simplest way to calculate it. We consider every possible failure, and we examine whether this failure leads into a guild. If it does, then the processes that remain outside of the guild are called a tolerated set. And the intuition is that the protocol, the rest of the participants could still make progress without these processes. And in this sense, the tolerated system summarizes the resilience of the whole ABQS. And what we prove in our work is that the tolerated system of an ABQS will always be a BQS. This means the Q3 condition will always be satisfied. And now that we have the tolerated system, we can go back to our example and actually perform the composition. Now the process C can use the tolerated system of the second ABQS to perform the Cartesian union. Now there is only a subtle case that I want to briefly mention. It could be the case that even though our ABQS satisfies the B3 condition and the tolerated system that we calculated and we saw that it satisfies the Q3 condition, it could, however, be the case that when we apply this pairwise Cartesian union, we can break the B3 condition in the resulting system. This can happen if there are common processes in the two ABQS. And what we can prove, however, is that if the B3 condition breaks, then the sets that actually break it will not be tolerated sets. So what does this mean? Since they are not tolerated sets, we can actually remove them from the fail-prone systems. We can have the processes remove these sets from their fail-prone systems. And this is what we call the purification procedure. The idea is that you might have your own beliefs, you might expect this set to fail, but if the failure of the set doesn't lead to a guild whatsoever, then you cannot protect it. You cannot protect from it, so you can remove it from your fail-prone system. And note, observe that this is a deterministic procedure. Every process can check the B3, can see which fail-prone sets break it, so this procedure can be performed independently, given that the test assumption of all processes are known. And with this, I would like to conclude the talk and thank you. I encourage you to read our blog post or our paper. Thank you very much.